Great. Yeah, I have to just say it is super cool that I heard a talk on string theory and it involved genetics. I mean, and I got to see a picture of DNA. Okay, so the next one, okay, this is great how people are voting. This is really neat. So for the next one, this is from Harrison Blake. And what is being asked is how did you do theoretical work in undergrad, or did you? When did you know? And then how did you set yourself up for graduate school to do theoretical work? And then there's a follow-up one which says, when did you know supersymmetry was for you?
Okay, I'm going to ask you to go through those questions one at a time because
yeah, let me say,
I often tell people I have one active brain cell remaining at
yeah.
70. So
Yeah, that was
let's
brutal.
start taking one at a time. Go ahead.
I guess one of the things, I think the first main question is as an undergraduate, were you able to get into doing theoretical work?
The answer is both yes and no. The answer is no, because I didn't have any, even though I was at MIT and I could have perhaps availed myself of REUs, research experiences for undergraduates, which was very popular. I was too shy in some sense. I was too frightened to approach a professor about doing that. Nonetheless, during the summer after my freshman year, I stumbled into the research experiences by accident. I had a job in an electronics firm, my summer job, and the job involved reading what are called network diagrams, circuit diagrams. And so I was working with a group of young engineers. I was this kid who just finished his freshman year at MIT. They would, in the morning, bring in a bunch of these diagrams for me to classify. I would get it done incredibly fast. And then I would just sit there because I had nothing to do. And so my supervisor one day came and said, "Jim, we've got a problem." And I said, in my first response, did I make a mistake in classifying some of the network diagrams? He's like, no, no, no. He says, my boss sometimes walks the floor here in the firm, and he sees this kid sitting here doing nothing. That's the problem. And so you've got to find something to do, because we're not going to give you any more. We're working at capacity once we have your input, so we don't have a way to speed up the input. So you need to find something to do. And so what I did is I brought in my book on differential equations, because during my freshman year at MIT, I had taken a course on differential equations. And so I basically retook the course, teaching it to myself. And then at the end of coming to understand some things, I wrote an equation that I had never seen in the book. And I asked, can you solve this problem? And I spent most of the summer working on this thing, deriving all kinds of things that were not in the book. And then in the fall, when I got back to MIT, I was able to get access, excuse me, that summer was in Orlando, Florida. I couldn't find any place that would access the differential equation I had written. But when I got back to MIT, I found this equation in a book. It's something called the Coulomb wave function. And I was amazed that working on my own, I had derived all these properties that were classified in this advanced mathematics textbook on this wave function. And that's when I understood that I could do theoretical research myself. And that's how it started.
Cool. Wow. Well, let me, because I think this is another neat question that it probably is for a lot of younger people listening, is the follow-up question here about how did you set yourself up for graduate school to do theoretical work?
Okay.
That's a nice question.
So I'm going to back that question out a little bit because it actually has a long tail. I first got interested in science when I was 4 years old. I was in Canada at the time. My mother took me to see a science fiction movie. For whatever reason, my 4-year-old mind glommed onto the idea that science was fun and adventurous. And so at age 4, the story goes, I came home and I tried to explain to my father how rockets worked. At age 8, I was having difficulty learning to read. And so my father remembered that his 4-year-old son was extraordinarily interested in space travel and rockets. And so my teacher suggested if my father would bring home some books on those subjects, I would learn to read much better, much more quickly. And arithmetic was never a problem in my family. As you know, Michael, because earlier today, I have 2 children that look like they're going to be physicists too. So we actually like math. I call it the family business for us. But reading was a challenge. And so these books on space travel, you know, I learned to read, but they also excited me even more about science because I learned about the size of the universe. Yeah, I was 16 when I had my first physics class. I learned about special relativity. I had a fantastic physics teacher who actually had a degree in physics, but was teaching high school, which is not so usual even these days. And so that's when I decided that I was going to be a physicist. When I graduated from high school, the high school I went to was a segregated, all black high school in Orlando, Florida. And my dream was I wanted to do physics. And I thought if I went away to college, I could get a degree in physics and maybe come back and teach at the local community college. When I got to MIT, my horizons suddenly brightened. I came to understand that essentially I could understand anything in physics that I set my mind to, including things like general relativity and quantum field theory. And I have a deep, passionate love for mathematical physics. And so it was in probably my second or third year as an undergraduate that I decided I wanted to go to graduate school and get a PhD because that was the only route I saw that would allow me to continue to be engaged with this material that I loved so much. So that's the complete story about me going to graduate school and winding up writing MIT's first thesis on supersymmetry.
Cool. Okay, so we have a ton of questions now. It is a massive list, but I'm going to probably be doing this by the voting. The next one, this is a good question for people. What is the difference between a fermion and a boson?
That is a great question. So let me try to give it to you. Okay, so I'm gonna have to use an analogy to waves. So if I had a string, so imagine I had a string between my fingers, then it could vibrate up and down. That's what we call the first harmonic. It could flip back and forth. That's a second normal mode. It could have 3 humps, 4 humps, 5. So normal modes basically count the number of lobes. So here's one upload, here's the one download. So that's an n equal 2 excitation. Now I can explain what's a boson and what's a fermion. Quantum mechanics tells us that particles behave like waves. So if you took one electron and put it inside of a box and asked what kinds of waves would be associated with it, what you would find is that any of those waves I described before with any arbitrary number of humps could show up in the description of the electron. If you put 2 electrons in a box, what you'd find out is that only 1/2 of those number of waves could show up. But if you put 2 bosons in the box, you would continue to find that the same number of humps could show up. So at a mathematical level, it's a question about how many wiggle ups and downs I can get from these particles when they are confined in pairs to a box. The other way I could say is that fermions are things that do not allow all the quantum numbers of separate fermions to be the same. It's the Heisenberg uncertainty principle. It's the thing that tells you that only 2 electrons fit at the lowest energy level of an atom, and that 8 electrons fit at the next level. That's the difference between bosons and fermions. If electrons were bosons, all of them would drop to the lowest level.
All right, that's cool. Okay, the next one is interesting. It's a little more technical. So here we go. Is there a way to use a type of backpropagation to calculate the ideal network connections and weighing to cut down on computation? And then there's a parentheses, but maybe should I leave it at that? I'll leave it at that.
Well, you can go parentheses. That's actually a very, very interesting question because that suggests that machine learning and neural nets might have space to work here. And so guess what I'm working on right now? That question, of course. One of my former students actually works for Google Search in New York. One of the students, not listed in my acknowledgements, but an undergraduate student that I worked with, I think about 6 years ago. His name is Matthew Hawkins, and Matt and I are right now working on a paper trying to look at this issue.
Cool. Okay. Well, there you go. So this is a great question because it still needs to be answered. Okay, so the next one is interesting. Having spent a large part of your life working on a theory of everything, what is your opinion on the Wolfram's Physics Project?
Oh my goodness. Well, first of all, I've known Stephen since 1980 when I went out to Caltech to be a postdoc in the group of Richard Feynman and Murray Gell-Mann. That's when I first met Stephen. And right now, Stephen, if you actually go, so Stephen has a channel on YouTube. If you go to that channel, you'll find out that I made a presentation there about 4 or 5 months ago. And so I mean, the reason Stephen and I are talking is because he's starting from objects called cellular automata. And we think they're going to bump into these graphs that I've been talking about, because in the way that he's doing things, the question was going to be, if you use an information theoretic foundation, how are you going to describe fermions? And in what we do, we've actually used the four-dimensional physics to lead us to networks where fermions are naturally described by this sequencing process that I was talking about. And so Stephen and I are talking. I had an exchange with Stephen about maybe a week ago.
Okay.
So I am watching. That's what I can say. I think there may be something extraordinarily interesting going on.
Okay, cool. Okay. And I'd encourage people to continue to vote. We have a lot of, we're starting to get to ones with a lot of ties, but
yeah. So let me give a shout out to my
sure.
my geneticist colleague Richard Linsky, who was, as I said, was on the webcast, and he made the comment, interesting, extremely interesting mix of fields and ideas. So thank Richard. And there are other folks I see that I know here too. So I'm glad I actually publicized this among my friends that we'd be doing this tonight.
Yeah, feel free. Do you want to reach out to anyone else in the chat there?
Yes, there's a friend named Edway Goins, who's a mathematician of all things at Pomona College, and he told me that he and possibly some of his students might be watching tonight also.
Okay, great. Okay, should I go back to another question? Maybe we can go. A lot of people are still hanging out. How are you doing? Are you getting pretty?
I'm okay. I
don't want to push it.
I tell people, I'm approaching 70 in December if I'm still around on the 15th. But I've been very fortunate in terms of my life trajectory. Apparently, I got pretty good genes because, like I said, I'm almost 70. I didn't abuse my body when I was young, so I didn't get heavily into drugs or cigarettes. And I didn't play I didn't do athletic endeavors that left me with broken bones and what have you. And for those of you who do that stuff, let me tell you, when you get old, that's going to come back and you'll remember it. And so I'm okay.
Okay. We'll do a few more questions and wrap up.
Okay.
I know it's been a long day, and we've taken up a lot of your time. So this next one is, if I understand what you've done correctly, you've discovered a sort of genetic structure underlying the theoretical mathematics of the universe. By analogy to biology, then, is it theoretically possible to use your structure to postulate other theoretically viable universal models?
Well, I think the answer is yes. And that comes closer to what Stephen Wolfram is sort of doing than what I've been pursuing. So one of the really weird things I didn't get to tell you folks about tonight, because it would just add to the length of the talk, is that error correcting codes are in these diagrams also. And I mean, I have a set of mathematical collaborators that I've worked on this with, and around 2011 in the period 2011 to 2014, we discovered that these things involve error correcting codes. Now, when you think about the genome, and I don't have to tell you this, Michael, when you talk about the genome and error correcting codes, it's the only, to my knowledge, and maybe someone else on here will be able to educate me, but to my knowledge, genomic structures are the only thing in natural science that I know about that involves error correcting codes. Not computer science, which is man-made, and not information theory, but in the natural science, that's the only place I see an overlap with error correcting codes and some structure. And so to me, this suggests, if in the work I've done, we found these error correcting codes are unavoidable. As soon as you do this sequencing process, it turns out the error correcting codes are hiding there also because of the way that the mathematical structure of these networks is formed. To me, the very deepest question is, why in the world would error correcting codes be in the mathematical laws of the universe? This is a question that I was first asked by someone in a public talk I gave maybe 10 years ago. And the only answer I have is that since in the natural universe, the only place that I know about error correcting codes is genetics. And if you ask geneticists, why do error correcting codes occur? The answer is evolution. And so for me, the deepest question is, how in the world could the mathematics for the laws of our universe be subject to evolution? And if they are, that then says that you could replay the kind of experiments my friend Richard Linsky is doing to look whether there might be alternative evolutionary paths to things that are like our universe. So this opens up an incredibly broad set of questions.
Wow. Okay, it's getting very deep. Okay, let's do two more questions, but I want to skip to this number 7 because I can't help it. With the biology side is, worry, because I love the fact that you've taken ideas from biology to then address fundamental questions in physics. So were you interested to read about biology out of your curiosity, and then the idea to use it in physics came up? Or did you think about the idea and then decide to read its details in biology?
So I'm a classically trained physicist, and that means that I had this physics question. It's a field theory question about M theory, as I described. But in 2004, when we started this program of what I call sequencing the equation, I immediately was struck by at least the surface level similarity to genetics. And so, for example, if you look at that teaching company video that I did in 2005, the name of it is Superstring Theory, the DNA of Reality. So in a general sense, I've been thinking about the nexus of ideas. And one of the things I didn't tell you folks about and didn't have time to show you is that something like folding, like protein folding, also applies to these networks I'm talking about. Not the twisting things, but there are other things that look very similar to protein foldings. And so I have been primed to think about biology and genetic models from the beginning of constructing these kinds of networks, because to me the similarities are just so striking. I have my son who, in fact, let me, since I'm going to call his name, let me get his image on my screen. My son is in graduate school and apparently working to become a biophysicist. And so I've been learning, the basic thing is I've been learning things about biophysics from my son, who's now in his second year of graduate school. And so he's my tutor. My son is actually my tutor when it comes to these sorts of issues. And I've been slowly learning from him. Let's see.
Are you able to share screen?
Yeah, I'm gonna try. Okay, so can everyone see my cursor circling these two people?
Yeah, that's
Okay.
great.
So that's my son and my daughter. My daughter studies black holes. My son studies biophysics. In particular, he's looking at cell motility under the impact of electromagnetic fields. And so he's my tutor, and that's kind of how I began learning about things like BLAST and what it does and what have you.
That is so cool. Okay, I think let's do one more. We'll do one more question, and we probably should wrap this up.
Okay.
So this one is now the top voted. So, can you recover the solved results of the simpler problem in string theory you mentioned via your sequencing library, the classical 2 equal to a Q? And this is where I don't know.
Yeah. So the answer is yes, but the answer was known before our library technique was developed. So we know how to reproduce it, certainly, but it's not, it's not a, how do I say this? It's a consistency check that what we're doing for these more complicated systems also work for these simpler systems.
Wonderful. Okay, I think we should let you, sign off, take a, relax, and
No, thank you.
but it was really wonderful. I know I'm speaking. You can see how many people have stayed around.
Yeah, we still got 175 according to the count.
I think people would love to hear more, but I think I would really appreciate you taking the time. It was a delight, and I think I speak for everybody that it was just wonderful having you here this evening, and we got to learn some really great new ideas about string theory. And I hope at some point, we can meet in person, and you can come to physics. So, visit Columbus again at some point.
Yeah. Well, as you know, I've been to Columbus before, and I'm looking forward to my return. Let me again thank everyone for your great hospitality and generosity, and especially persistence for people who at 9:30, a lot of people who probably have homework to go do, are still here listening to a crazy old physicist talk about his fun toys. I'm going to make an offer now, Michael, that I probably shouldn't, but if anyone in the audience has a really pressing question they would like me to address, if they will send them to you and you will bundle them up and send them to me, I will try to make time to respond.
Well, great. Yeah. So yes, we'll definitely do that. And maybe I can work with Terry to maybe there's a huge number of other questions to try to organize some of that.
Yes, if you could, if you could curate that process, because I'm sure that some of the questions probably overlap in some sense, and I'm not looking, to.
Right, you don't want a huge list, which
absolutely.
That's right. I want it as compact as protein folding will allow.
Oh boy. Okay, we'll do our best.
No, we will definitely snag those, and thank you so much. That is a very, very generous offer, which we will take you up on.
Okay.
All right. Well, Jim, thank you so much again, and have a wonderful evening.
Thank you so much. Take care.
Good night.
Good night.